Okay, we'll conclude the day with a talk which will be a bit different from all the talks that we've heard so far, because it's not a talk about a research project, it's a talk about teaching. And I would like to thank the organizers for accommodating this talk, and I would also like to thank you for sticking around. I take this as a good sign that you are interested in teaching and that you find teaching important, and I'm assuming that most of the older people in the audience actually do teach. And I'm particularly happy, however, about the younger people who are sitting in the audience, because in your case probably it hasn't been a long time since you attended quantum physics courses, and I would be particularly interested and curious about your feedback on the idea that I will present here. Ideally, teaching and research should be cross-fertilizing. Research should stimulate teaching, make teaching interesting, topical, prepare young people for future research projects, prepare them for the demands of the wider labor market. And reversely, teaching should be very stimulating also for the teacher and stimulate new research ideas. And in the previous talk we just saw a beautiful example how the teaching of rational mechanics stimulated an interesting research project. And what I would like to convey to you, though, is that especially with regards to quantum physics, there has been a growing disconnect in recent years. I'm not talking about specialized courses on quantum computing, quantum information science, and many other modern topics that are being offered at many universities, but I'm actually talking about the basic introductory course to quantum physics, which in many places is still taught more or less the same way it was taught 20 years ago, 30 years ago, 40 years ago. And I think there's a growing disconnect with the demands of the outside world for two reasons. One reason is regards the topics that are of current interest. And I'm thinking in particular of the explosive growth of quantum technologies in the past 20, 30 years. When I talk about quantum technology, I mean, of course, quantum computing, I mean quantum simulation, sensing, and communication. And this is these are fast-growing fields, and rarely do they enter into the introductory quantum physics course. The other aspect why I believe there's a growing disconnect is that also the audience is changing of quantum physics courses. Precisely for the same reason why these topics are becoming more and more important, we have more and more people wanting to learn about quantum physics who are not physicists or physics students in the traditional sense. With all these, this is now also heavily commercialized. Many companies are entering quantum technologies. There's a strong demand for people well educated in these fields. And earlier this year, I attended the European Quantum Technology Conference, and there was a very interesting talk by Cecile Merzbacher of the American Industry Consortium, Quantum Industry Consortium, and they had conducted a labor market study, and they screened job postings. So what kind of profiles are in demand in the wider field of quantum technologies? And you see here a long list of different profiles with profiles that are very different from the traditional physics PhD. And you have here technical sales marketing, even product sales marketing, circuit designer, software programmer, and so on, all in the field of quantum technologies. And then on the horizontal axis, you see the kind of degree that was demanded, that was expected. And you see here a lot of profiles where no PhD or physics PhD was needed, but bachelor and master degrees. And so you see there's a huge demand for skilled labor in the field of quantum technology, which falls outside the traditional physics education at the university. Now, if you think about how a traditional introductory quantum physics course is set up, mostly we still begin with, I don't know, double-slit experiment, wave-particle duality, Schrödinger equation, hydrogen atom, potential wells, and so on. But what really is interesting for these fields are questions like that. What is quantum technology at all? What's the basic physics behind it? What does a program, what does an algorithm, a circuit for a quantum computer look like? How can quantum effects protect privacy? I'm thinking of the quantum cryptography protocols and so on. Now this implies that in introductory courses, these questions should be dealt with, and instead others can be postponed to a later date. So, for example, you don't have to learn time-dependent perturbation theory necessarily in an introductory quantum physics course, but you really should learn something about Bell's inequality and the violation of it much earlier than is traditionally taught, because if you want to understand, for example, the EPR protocol for quantum cryptography, quantum key distribution, then you have to know about Bell's inequality. Yeah? So it calls for a reshuffling and a redesign of introductory quantum physics courses. And I would like to report briefly about a course that I taught for the first time last semester at my university. That's the University of Applied Sciences, RheinMain University of Applied Sciences, close to Frankfurt. It's essentially an engineering school. And there's also a physics curriculum, and I did have some physics students in the course, but I had lots of electrical engineers, computer scientists, applied mathematicians, mechanical engineers. So a really diverse audience. And the challenge was to convey all of that in a manner that is accessible to this diverse audience. And at the same time, not superficial, but with some substance to it. So that course, this is very unfamiliar for a theorist because we actually showed some experiments. That was a new experience for me as well. So we had experiments, we used simulation tools like the IBM Quantum Composer to design and also run simple quantum algorithms. The highlight was an excursion to the research center in Jülich, where we actually saw a real quantum computer under construction. And then, of course, there's the theory part. And that's the part that I would like to focus on in the remainder of this talk. So what kind of theory can you do in such kind of course? In all of this, I had to keep it very simple, given the diverse background and given the fact that many people didn't have a classical physics education that they could build on. So in terms of mathematical prerequisites, all that was really needed was that people knew what the vector is, what the matrix is, what a complex number is, and what the probability is. That was basically all I required. That's what you learn even in engineering curricula. That's what you learn in the first year. But I didn't require any physics knowledge. Now, what was the basic philosophy, the basic approach to this course? The first one I already mentioned, keep it simple. What does that mean specifically? Everything is done in a finite dimensional Hilbert space. So, we start with the qubit, which is two-dimensional, so that's the smallest you can get, but it never becomes infinite dimensional. And we only look at discrete transformations, so there's no continuous time parameter, there are no differential equations, which simplifies a lot the mathematics. A second basic tenet is visualize as much as possible. That makes it very tangible for engineers in particular. Pictorial models, games and simulations, and very early on we introduced quantum logic gates, and we worked a lot with these gates. And finally, what I already mentioned, you have to address the conceptual issues very early, because I wanted to discuss, for example, the EPR protocol. So imagine you have a group of engineers, maybe second year, third year students, never had any physics course before, maybe except for mechanics, and now explain to them Bell's inequality. That's a bit of a didactical challenge. Now the key concepts here, of course, that you have to introduce are the measurement process and entanglement. These are two very basic ingredients. And just want to give you a slight flavor of how this looks like, and if you are interested, I'll be very happy to talk more about this then after the lecture, over dinner tonight, as you like. So, I already said we start with two-level systems with experiments, measurements that have only two possible outcomes, and the two specific physical systems that are most adapted to that are, for one, the polarization of light. So you can illustrate that with polarization filters or with polarizing beam splitters, and the famous Stern-Gerlach experiment. Now these are examples of binary measurements where you have only two possible outcomes, in the case of a filter, pass or not pass, splitting with a beam splitter, or up or down with a Stern-Gerlach. And I'll introduce a slightly abstract notation that subsumes these specific cases. So you have here your splitter, whatever it is, and you have two possible outcomes, 0 and 1. All of these can be continuously rotated. You can rotate the polarization filter, you can rotate a beam splitter, you can rotate the Stern-Gerlach experiment. So you have a continuous parameter, an angle. There's a factor of 2 here. That's because if theta is 360 degrees, you want to have a physically equivalent measurement, and you can show that with these definitions. And one of the first insights that you convey is that these splittings that you get in these binary experiments, they are not just random splittings, but they are actual measurements in the sense that they are reproducible. So if you have such a binary experiment with an arbitrary orientation angle theta, and you block out one of the beams and then you repeat the same measurement, you get with certainty the same result. So it's not a random splitting, but it's an actual measurement. Then you start to rotate the two against each other, and then of course it's you no longer get with certainty the same result, but you get two peaks here, and their relative intensities are proportional to the conditional probability that a particle will pass the second splitter in the upper beam, given that it passed the first one in the upper beam. And in the course we did that sort of experimentally and with simulation tools, and looked at the various different data points, and you get this curve. And another important insight for the students is that regardless of the specific system that you use, whether you use polarization filters or Stern-Gerlach, it's a universal function. It's always the same. And talking about visualizations, there's a nice visualization that maybe many of you are familiar with. A circle model to calculate these probabilities when you remember these data points here for this universal curve. Now, presume you want to determine this conditional probability here at 45 degrees. Graphically, what you can do, you take a circle with diameter 1, and then you, from the north-south axis, you take the angle 45 degrees, you get this point here, and this gives you exactly the conditional probability at 45 degrees. That's of course just the Born rule behind that, but it's a nice mnemonic device for the students. Okay, I have to be very fast, so I won't do this in detail, just the keywords. Another important concept is that the order of measurements is important. That's of course a key insight of quantum physics, the non-commutativity, non-compatibility of measurements, which you can show very nicely with these binary experiments. You can introduce the preparation of a state. You can define the concept of a state. What is a state? It's, on the one hand, it's the result of a preparation, but on the other hand, it also determines the future probabilities or the probabilities of future measurements. So you introduce the concept of a state, and it's all done pictorially, without any mathematics at that point. Then we introduce the notion of qubits. Again, starting with this circle model. Of course, we all know it's actually a sphere, it's the block sphere, but there's a lot you can do and you can explain already with the circle model. You can introduce measurements, you can visualize them pictorially as axes through the circle or later through the sphere. You can visualize the change of the state after a sequence of measurements step by step. Here on the circle model, you can introduce transformations. We all know these are unitary transformations in Hilbert space, but pictorially in the circle model, these are transformations which leave relative angles invariant, and there are two types, either reflections on an axis or rotations. These are the two types of transformations that you can have. And in this way, you can even introduce gates, single qubit gates, without Hilbert space. You can say, in the circle model, the Pauli X, for example, is a reflection on the horizontal axis, the Z gate is a reflection on the vertical axis, and so on. So it's all pictorial. You can introduce controlled gates, either classically controlled or qubit controlled. You can introduce the C0 and so on. It's all pictorial. And I'm sorry about the speed, but that's of course due to the time constraints that I have. I just want to mention that you can, using these pictorial tools, using the gates introduced in this way, you can show that there must be something like entanglement. You can introduce the C0 gate, require that this is a transformation, and just by considering conditional probabilities for various possible inputs and outputs of the gate, you can conclude there must be something like entanglement. Okay, many slides, many pictures. I just show you the very last one. So maybe after 3 or 4 weeks, I reached the point where I can actually discuss the Bell experiment again in a purely pictorial way. You know the usual setup with Alice and Bob, and they have two observables at their disposal that they can measure. The observables are visualized by axes through these circles. And we discussed the CHSH, the usual Bell inequality or the CHSH inequality, the fact that this is experimentally violated, and you can actually, using only these pictorial tools, using this circle model for the conditional probabilities, you can actually determine your expectation based on quantum theory and see that it violates the CHSH inequality. I'm sorry that I had to run so much. Thank you very much, and as I said, I will be happy to discuss more and explain more over the next minute.
Any urgent questions? Please.
Thank you. That was a lovely talk. But can I just ask, so you did introduce the tensor product in the end, did you? I see it up there.
Yeah, you see that there. I didn't introduce it formally. No, I didn't.
But just on that, I mean, the mathematical manipulations involving it are very elementary.
Yes, yes. So I could have. I could have. But you know, this is all before I introduce Hilbert space. I eventually do introduce Hilbert space, but actually after that.
Short question: do you have any return from students, whether they like it or not? Did you teach it already?
Yeah, I taught it last semester.
Okay, and so did you ask students whether they like it, whether they...
Well, we have in our university, we have a mandatory evaluation of each course, and I was happy with it.
Sorry?
They were happy with it, and I was also happy with their evaluation.
Okay. Last thing for the speakers.